Hello everybody, Root Beer here. I thought I'd start another series based off of a contest released by the Center for Education in Mathematics and Computing. So I thought we'd start taking a look at the Galois contest. That is the 10th grade level Canadian written contest, not to be confused with the Galois, which is the multiple choice contest. This one requires actual explanation and proofs and justification for every single one of your answers. Okay? So we're going to start off with the very first Galois, the 2003. Now, in the year 2003, they just introduced the Friar, the Galois, and the Hypatia. So the Friar is the grade 9, the Galois, which we're going to go through, is the grade 10, the Hypatia is grade 11. And these are written contests, in contrast to the Pascal, Cayley, and Fermat, which are the multiple choice contests. And these three, the Friar, Galois, and Hypatia took the place of another paper called the Descartes, which ended in 2002, which was another written contest. So they were just starting out with these papers, and the Descartes was a very advanced level of paper. It was sort of grade 13 or upper 12th year sort of math. So they didn't quite exactly know what they were looking for and what format they wanted, which is why, and I think I noted this in the Friar video, there are these problem extensions. Now, they don't appear in the 2004 paper or 2005 or anything else. There are these problem extensions. They're sort of like, well, you'll notice every question has sort of A and B, but it doesn't really have a C or a D. Question 2 has a C. And so these were meant to be harder parts of the problem that were sort of answer the main contest, and then if you can, move on to the extensions. Whereas they have now sort of just included any harder parts in the actual question. So I'm going to be avoiding the extensions just because, you know, it's not a format that we're going to need to get used to if you're actually trying to do Friars, Galois, or Hypatias. But if there's enough of a demand for this, I will go back and actually go through the extensions. They're not particularly difficult. It's a portion of the contest that they didn't continue on with, so I'm not going to treat it as canon, I guess. Alright, so with all that preamble out of the way, it is the grade 10 contest. We are going through the 2003 Galois paper, so expect 10th grade level math to come into it. And let's get cracking on question number 1. By the way, if you would like a copy of the contest, you can click a link in the description for this contest, and you can also go to the CEMC website, CEMC, and you can download other Galois. I will be going through other Galois papers, and you can see their solutions, and you can actually go through and register your school or get a teacher to do that on the very same website. So there's a little plug for the University of Waterloo right there, because without those guys, I wouldn't be producing this sort of content. So. And if you don't like my solutions, by all means, go ahead and read theirs. Sometimes there are multiple solutions. All right. Question number 1, 1A. The sum of squares of 5 consecutive positive integers is 1,815. What is the largest of these integers? All right, so we have 5 consecutive positive integers, and we square them, and it adds up to 1815. And we want the largest of these integers. Okay. So there's a couple ways to do it. Since there's 5 of these consecutive integers, we could pick out the middle integer, n, and say our range is n minus 2, and then n minus 1, and then n plus 1, and n plus 2. And we could square each of those and have them equal to 1815, and eventually be able to argue and figure out what n is. But n would be the middle number. So instead what we're going to do is we're going to say n minus 4 plus n minus 3 plus n minus 2 plus n minus 1 plus n, 1815, and we're going to square these guys. So now we pretty clearly have 5 consecutive integers, but we have the one that we want, the largest one, distinguished here. Okay. Now what we're going to do is we're going to use sort of FOIL or other techniques to expand these out, and then we're going to get a bunch of things in terms of n and n squared and some constant terms, and then we're going to rearrange it and see if we can solve for what n is. Okay, So this one, however you do it, comes out to be n squared minus 8 plus 16. Then we have n squared minus 6n plus 9, n squared minus 4n plus 4, plus n squared minus 2n plus 1, plus n squared is equal to 1815. Okay? So let's get to grouping some things. We have 5 n squareds here. And minus 8, minus 6, so that's minus 14. Minus 4, so that's minus 18, so, and minus 2, so that's minus 20. N. And then 16 plus 9, that's 25. Plus 4 plus 1, that's another 5, so that's 30. Is equal to 1815. Okay. Now something I immediately notice is that each of these terms has a factor of 5. There's 5 here, 20 is a multiple of 5, 30 is a multiple of 5, and 1815 is a multiple of 5. So instead I could just divide by 5. I get n squared minus 4n plus 6. And I grabbed my calculator because off the top of my head I don't know 1815 divided by 5. 363. Okay. Now if I bring this 363 over to the other side, 363 and 6, so it should be 357 and equals 0. Now, there are other ways we could have done this. We could have chopped off a 2 from this 6, moved it over to the other side, and said n squared minus 4n plus 4. Well, that happens to be n minus 2 squared. And that might have done the trick there, and we would have had n minus 2 squared is the same as 361, which is 19 squared. But we go with our tried and true method here, which is rearrange things and get to a quadratic formula, because we know how to solve quadratic formulas. So n is negative b, so 4, plus or minus square root of b squared minus 4a, which is 1, times c, which is negative 357, all over 2a. Okay, so that's 4 plus or minus. And now we have 16. This minus and this minus will become a plus. And 357 times 4, that's 1428, all over 2. 4 plus or minus, and it'll still all be over 2. Square root of 1428 plus 16 is 144. Okay. And that happens to be 38 squared when we work that out with our calculator. So 4 plus or minus 38 all over 2. Well, that's going to be 2 plus or minus 19. So that's 21 or negative 17. But our question specifically says that these are consecutive positive integers. So n, the largest number, is 21. Okay, we just double check. It's always a good idea to double check exactly what they're asking for. What is the largest of these integers? Okay, we do have the largest one. And the way we set up our equation, we were definitely going to get the largest one. That's why we chose to do n squared, and then n minus 1 squared, and n minus 2. N is the largest of all of these 5. So when we solve for n, we definitely will get the correct answer here, the largest integer, as opposed to some of the other numbers which we could have solved for. We could have started with n and n plus 1 and n plus 2 and n plus 3 and n plus 4. And then we would have solved for n, which would have been the smallest of the integers, and then we would have added on 4 to get our final answer. So there's lots of different approaches, as I've been hinting at. So that's A part. And B, the last part of question 1, Show that the sum of the squares of any 5 consecutive integers is divisible by 5. Okay. Well, we actually already remarked that. It was a verbal remark, but over here, 5n squared minus 20n plus 30, well, that's just us completing the sum of these 5 squares. So 5 integers squared minus 1 squared plus n squared. We showed that that was equal to 5n squared minus 20n plus 30, which is 5 times, what do we have here? N squared minus 4n plus 6. So clearly we have a factor of 4 here. And the sum of the squares as a factor of 5. So I think that's pretty quick to show, and no matter what route you took, when setting up this first sum of 5 consecutive squares equation, you would have rearranged and solved, and you would have had an expression for the sum of the 5 squares you chose. Whether you started with n plus 1, n plus 2, or n minus 2, n minus 1, n plus 1, n plus 2. No matter what you did, somewhere in your workings, in part A, you would have stumbled across this formula, and it's not that hard to realize, oh, I can just take out a factor of 5, and everything works. So that's question number 1 on the 2003 Galois. And in the next video, we'll take a look at question number 2. So I hope to see you guys then.